Hello everyone, welcome to my YouTube channel. In this video, we will be discussing about the concrete mix design by Indian Standard Methods, that is commonly known as IS method. The method follows the code IS 10262. Concrete mix design can be performed by IS method following these 7 steps. Let's get into the problem and use these 7 steps to solve a given problem. You can see the problem in the screen. We are given the characteristic compressive strength of concrete required at 28 days. Characteristic strength is nothing but the value of compressive strength at 28 days, which 95% of the samples are expected to exceed. In other words, no more than 5% of the samples can fall below the value of the characteristic compressive strength. Similarly, in the question, we are given the maximum size of aggregate and also the shape of aggregate. Similarly, we are given the degree of workability, which equals to 0.9 times the compacting factor. The degree of quality control is good. The type of exposure is mild. Similarly, we are given the specific gravity of cement, coarse aggregate and fine aggregate. And also the zone of sand is third. At last, we are given the moisture condition of the fine aggregate and coarse aggregate. For fine aggregates, the water absorption is nil and the free moisture content is 1.5%. Similarly, for coarse aggregate, the water absorption is 1% and the free moisture content is nil. Let us now use those 7 important steps to solve this problem. In step 1, we determine the target mean strength Ft. In order to achieve the condition that no more than 5% of the samples are allowed to fall below the certain value, that is 20 MPa in our case, we set our target slightly higher than the characteristic compressive strength, and this value of target mean strength can be calculated by using the formula Ft equal to Fck plus K times sigma, where Fck is the characteristic strength, Ft is the target mean strength, K is a constant and it is equal to 1.65 for the condition which we are taking into consideration. That is 5% of the test results are only below the characteristic strength and no more than that. Sigma is the standard deviation. Sigma is equal to 4 for M20 and M25 grades of concrete. For lower grades than M20, that is like M10, M15 or lower, sigma is 3.5. Similarly, for higher grades than M25, for example M30, M35 and higher, sigma is 5. In our case, since Fck is 20, so we choose the standard deviation to be 4. Using these values, we can calculate the target mean strength. Therefore, Ft is equal to 26.6 megapascals. In step 2, we determine the water-cement ratio and check it with the maximum value of water-cement ratio from the durability conditions. If the type of cement is not specified, we will use this curve. Mark the target strength in the y-axis and draw a horizontal line up to the curve. And then draw a vertical line to meet the x-axis. This gives the value of water cement ratio. Therefore, water cement ratio is equal to 0.5. However, if the type of cement is specified, we will use these curves. Sometimes the question may not directly mention the type of cement, but instead give the compressive strength of cement. In that case, we can choose the type of cement using its compressive strength using the table shown. It is important to keep in mind that we are talking about the compressive strength of cement and not the compressive strength of concrete. For example, if the compressive strength of cement is known to be 35 MPa, then the type of cement will be A, since 35 lies between 31.9 and 36.8. Now the curve for the same cement type is chosen, and using the target strength, the water cement ratio is found out similar to the previous case. In our case, since no information is given about the type of cement and also no information about the compressive strength of cement, so we will use the first curve and our first value, that is water cement ratio equal to 0.5. The water cement ratio thus obtained needs to be checked for durability conditions. For that, we should know about the exposure condition and the type of concrete, whether it is PCC without steel or RCC with steel. By question, the exposure condition is mild, and assuming it to be plain concrete PCC, since no information is given related to the bars. For mild exposure condition and for plain concrete, we get the maximum free water cement ratio to be 0.6, which is higher than our calculated value of 0.5. Hence, our value is OK, and we choose the water cement ratio to be 0.5. In step 3, we determine the entrapped air in 1 meter cube of concrete. Depending upon the maximum size of aggregate, we can choose the volume of entrapped air, which will be subtracted from the total volume of concrete to obtain the volume of other constituents. In our case, the maximum size of aggregate is 20 mm, hence volume of entrapped air is equal to 2% of the volume of concrete. For 1 meter cube of concrete, the volume of entrapped air will be equal to 2% of 1 meter cube, that is 0.02 meter cube. Therefore, volume of other constituents will be 1 minus 0.02 equal to 0.98 meter cube. In step 4, we select the water content W and percentage of sand in total aggregate P. This is the most crucial step in mixed design by IS method. We determine the water content and percentage of sand in total aggregate using one of these two tables. For concrete grades up to M35, that is M20, M25, M30 and so on, including M35, the first table is used. For concrete grades above M35, that is M40, M45, etc., the second table is used. These tables give the value of water content and percentage of sand for specific conditions. Table 1 gives the values for the following conditions. For shape of coarse aggregate to be angular, zone of fine aggregate to be zone second, workability value of compaction factor equal to 0.8, which equals to the 30 mm slump approximately, and water cement ratio of 0.6. Similarly, table 2 gives the values of water content and percentage of sand in total aggregate for the following conditions. Shape of coarse aggregate angular, zone of fine aggregate second, workability value equal to 0.8 compaction factor or 30 mm slump approximately, and a water cement ratio of 0.35. For any departure from above mentioned conditions, corrections have to be applied as per table 3. In our case, for M20, since 20 is less than 35, table 1 is used. For 20 mm maximum aggregate size, we can see the water content is equal to 186 kg and percentage of sand is equal to 35%. Let's find out which corrections to apply and which not. The conditions for table 1 can be seen in the screen. By question, the aggregates are angular, hence A condition is satisfied, so no correction for it. Similarly, by question, the fine aggregates conform to the zone 3rd, but table 1 assumes it to be of zone 2nd, hence correction is needed for it. Similarly, by question, the degree of workability required is 0.9 compaction factor, but table 1 assumes it to be 0.8, hence correction is required for it too. Further, we get the water cement ratio as 0.5, but table 1 assumes it to be 0.6, hence correction is needed for the water cement ratio as well. Now we write a correction table. It is clear from the figure that for sand conforming to zone 3rd, the water content remains unchanged and the percentage of sand is decreased by 1.5%. Also, the compacting factor in our case is 0.9, which is 0.1 higher than 0.8 as assumed for the table. For every 0.1 increase or decrease in the value of compacting factor, the water content is to be increased or decreased by 3%. That means, as our compaction factor is 0.9, which is 0.1 higher than 0.8, so we need to increase the water content by 3%. Or you can simply use the formula compaction factor minus 0.8 by 0.1 into 3% to determine the correction of water content for workability. Here CF is the compaction factor for our case, which is 0.9. Therefore, 0.9 minus 0.8 by 0.1 into 3 becomes 3%. Also, there is no correction for the percentage of sand. Similarly, for each increase or decrease in water cement ratio by 0.05, the percentage of sand is increased or decreased by 1%. Here also, you can use the formula W minus 0.6 by 0.05 into 1% for up to M35 grade concrete and W minus 0.35 by 0.05 into 1% for higher grades of concrete. For M20, correction equal to W minus 0.6 by 0.05 into 1%. In our case, W is equal to 0.5. Therefore, 0.5 minus 0.6 by 0.05 into 1 becomes minus 2%. Also, there is no correction for water content in this case. Since our aggregates are angular, so no need to perform the last correction. If our aggregates were rounded, we would decrease the water content by 15 kg and we would decrease the percentage of sand by 7% as seen from the table. In this case, these values would be 0. Add up all the corrections for water content and sand percentage. The total correction in water content is 3% and the total correction in the percentage of sand is minus 3.5%. We have water content equal to 186 kg and the percentage of sand equal to 35%. Applying these corrections thus obtained, the corrected water content becomes 186 plus 3% of 186, that is 191.6 kg. Similarly, the corrected sand percentage becomes 35 minus 3.5, that is 31.5% or 0.315 as a fraction. This completes the step 4. In step 5, we determine the cement content, that is C. We know water cement ratio is equal to water content by cement content. Therefore, cement content will be equal to water content by water cement ratio. Thus, we obtained cement content to be 383.2 kg per meter cube. We need to check this cement content from the durability conditions as done for the maximum water cement ratio. For mild exposure condition and for plain concrete, the minimum cement content is found to be 220 kg per meter cube. Which is the minimum cement content required. Since our value is higher than this minimum value, so our cement content will be equal to 383.2 kg per meter cube. In step 6, we determine the coarse and fine aggregate content Ca and Fa respectively. Coarse and fine aggregate content can be determined using the following equations. A is the absolute volume of fresh concrete, that is gross volume minus volume of entrapped air. If 1 meter cube of gross volume is taken, then the percentage of entrapped air was obtained to be 0.02 meter cube. Therefore, the absolute volume of fresh concrete B equals to 1 minus 0.02 equal to 0.98 meter cube. W is the water content or the mass of water per 1 meter cube of concrete. C is the cement content or the mass of cement per meter cube of concrete. Fa is the fine aggregate content. Ca is the coarse aggregate content. Sc is the specific gravity of cement. S of Fa is the specific gravity of fine aggregate in saturated surface dry condition. Sca is the specific gravity of coarse aggregate in SSD condition. P is the proportion of fine aggregate to the total aggregate. We have P equal to 0.98 meter cube, W equal to 191.6 kg per meter cube, C is equal to 383.2 kg per meter cube, Sc equal to 3.15, Sfa and Sca equal to 2.6 and P equal to 0.315. Using these values, we can calculate Fa and Ca respectively. Therefore, we obtained fine aggregate content equal to 546 kg per meter cube and coarse aggregate content equal to 1188 kg per meter cube. In step 7, we apply the necessary correction for moisture content and water absorption. While carrying out mix design, it is assumed that the aggregates are in SSD condition, that is saturated surface dry condition. You can see from the figure what exactly is the saturated surface dry condition. However, in reality, they are seldomly in the SSD condition. For cases other than SSD condition, appropriate corrections need to be applied to the calculated water content and aggregate contents. For water absorption by the aggregates need to be added, and free moisture content of the aggregates need to be subtracted from the calculated values to get the final corrected water content. The process is exactly opposite for aggregates. For the aggregates, water absorption needs to be subtracted and the free moisture content needs to be added to the calculated values to get the final corrected values. The values of cement content, water, fine aggregate and coarse aggregate obtained so far can be seen on the screen. Let's apply the correction for moisture content and water absorption. To obtain the corrected water content, add the water absorption for the coarse and fine aggregate and subtract the free moisture content of coarse and fine aggregates. For corrected coarse aggregate content, we need to subtract the water absorption of coarse aggregate and add the free moisture content of coarse aggregate. Similarly, for the fine aggregate, we need to subtract the water absorption for fine aggregate and add the free moisture content for fine aggregate. It is important to note that while calculating the corrected water content, the values for both coarse and fine aggregates are used. But while calculating coarse aggregate, only the values for coarse aggregates are used, and similarly while calculating the fine aggregate, only the values for fine aggregates are used. Let us list out the final corrected values. Hence, the ratio of cement is to fine aggregate is to coarse aggregate becomes 383.2 is to 554.2 is to 1176.1. Let's make cement 1 by dividing each of these values by 383.2. Therefore, the corrected proportion obtained is 1 is to 1.446 is to 3.069, which is the required design mix. Make sure to like the video, share it with your friends, and subscribe the channel if you want more such videos in the future. Also, feel free to ask any questions in the comment section. You can also mention any topics that you would like me to make videos on in the near future. See you in the next video.